Welcome everyone to the final keynote of today's GeoInform sequence of matters. I appreciate that everyone will already be a bit tired from a long day. When we welcome our keynote speaker, Orhun AYDIN, we have to appreciate that it's very early morning I guess you're on Pacific Standard Time, so that means some 9 hours or so. And thank you, and we appreciate very much that you make it such an early start into this day in order to introduce this topic. A topic, and that just focus on the spatial data science item here, which is clearly of increasing importance in our domain, in our field, in geographic information science and geoinformatics, which is a term we use a bit more here on the European end of things. Orhun AYDIN is actually teaching, so he's a fellow professor in a way, in one of our partner universities, University of Southern California, where we share quite a few interests and share our distance learning program. As well, the SSI, the Spatial Sciences Institute, is one of the real outstanding institutions in our field. So we are kind of academic colleagues, but I understand your day job is as a senior researcher, senior scientist on Esri's spatial statistics team, and with a background of graduate degrees from the Stanford School of Earth Sciences. It's quite clear that you bring a strong spatial focus, and as we all have learned over the past, that it's not only spatial, it's temporal as well. So spatio-temporal analysis is where we are going today, and that's why the world's problems are not easy, but they are complex. And as we have all been learning these days, they are not getting any easier. With that, I'd like to switch it over to you. Please just feel free to add any personal intro items you would like to add. The screen of the channel is yours. We're looking forward. Orhun?
Thank you, Joseph. It's a pleasure to be virtually here with you today. And I again would like to thank Professor Strobel for his kind invite for this talk. Today's talk is about the rise of spatial data science and machine learning, and how the spatial approach has been shaping our planet in terms of modeling, planning for, and understanding spatial and spatiotemporal phenomena. So that is what I will talk about today. Joseph already gave a great intro. I'm very grateful for that. So I just want to do a very small intro about what I do and why I'm so passionate about this topic. What you see here is just a figure from my PhD research, where I studied modeling uncertainty related to faults in the Nankai Trough in offshore Japan. We worked on a spatial process model, point process model, that can model different fault networks under limited knowledge and under limited geological understanding as well. And this is reminiscent of many problems we have. We have sometimes limited data. We definitely have limited understanding, especially about anthropological processes. So we need to have some spatial model to represent uncertainty. And then, as Joseph mentions, I moved to a small town in California called Redlands to work for ESRI's spatial statistics team, where I work on theoretical work to develop tools for the spatial statistics toolbox. This includes doing some research into spatial and spatiotemporal data scientific methods. And in addition, we also work on hands-on research to apply these methods to world's important problems. This is an example from modeling seagrass habitats that I will talk about later in the talk. And as Joseph mentioned, lastly, I also teach and do research in the Spatial Sciences Institute of USC, where we are very invested in spatial and spatiotemporal data science. And I would like to thank all of you for attending this late plenary. I really appreciate all of you being here. And you might have very diverse backgrounds. You might be city planners, geodesigners who make sure that our trains run on time, or hydrologists who design water wells for communities in remote areas. You might be working with precision agriculture, which is a very growing area right now. or you might be working on COVID-19 modeling and making sure that we have sufficient resources in terms of hospitals for people who need care. And I think this is the power of what we all do. We do very diverse, we seek very diverse answers to very different questions. We are from very different backgrounds, but there is this one dimension that ties us together, which is space, and also more and more, as Joseph mentioned, space and time. So this is very exciting to talk about the rise of spatial machine learning in this regard. So this is the outline of the keynote today, and I will talk about 3 distinct sections: why the spatial data science is so important, why it's on the rise, and how it is being implemented today. I will talk about spatial data science methods, but we know that analysis is only powerful if there is data. So in the second part, I will talk about a little bit about open data. And at SG, we also refer to this as the planet's memory, kind of building this memory of this open data source that people can leverage to solve spatial data science problems. And of course, when we bring together spatial data scientific methods that can turn this this planet's memory, so to say, into action, then we basically have a nervous system for our planet. Then whenever a global pandemic like this, for example, happens through spatial data science, through evaluation of this data, we actually can create set of actions, kind of like what a nervous system does. It will induce an action for us to do the right decision. And these will be the pieces of today's talk. So I will first start with spatial data science. There are many terms about that's being used about data science, machine learning, and analysis in general. And I just want to quickly go over basically what these all are and how they kind of fit in together. And I will talk about how spatial data science really fits in. Of course, when we watch a machine learning YouTube video or when we watch a machine learning presentation, we see a lot of terms. There are a lot of terms out there. There are a lot of buzzwords. But if we simplify these terms, we kind of keep on hearing artificial intelligence, machine learning, and deep learning. They are generally used as buzzwords, and the scope of AI is disputed and it's constantly changing. But basically, one way of thinking about this is kind of imposing human intelligence on machines through rigorous methods. And with machine learning, we know that these are data-driven algorithms and techniques that enable parts of artificial intelligence directly from data so that a machine can make decisions using these set of methods and extract some knowledge from data. And deep learning is just a set of techniques under machine learning methods. These are in particular to deep neural networks that can extract certain type of information. They are very flexible. They can be used on different data types. And when we think about how they relate together, they are kind of subsets of each other. And so this is kind of how they all fit together. And we think about this kind of outer ring, the artificial intelligence without machine learning. And I think in order to frame what machine learning does, what data science does, and also what spatial data science does, it's important to understand what these other pieces are. And I was very curious about this artificial intelligence piece a couple of years back when I was teaching this. And the deeper I dug in where artificial intelligence kind of originated, this actually comes from a conference held in Dartmouth back in 1960. And the professor who coined the term artificial intelligence is actually, his last name is McCarthy. What they wanted here was a set of predefined logical operators to do certain tasks. And in the past, people defined these knowledge bases. So this is artificial intelligence without machine learning. And in this area, they had models called CYC. Some of you might be familiar with CYC and Centric nets because they had applications to environmental sciences. What these are is basically a set of rules. For example, if you would like to predict extreme weather events, instead of finding patterns in the data, you define the rules yourself. You will say that if temperature is above this level, if this is the vorticity level, if this is humidity, then tag this particular raster cell as an extreme weather event. So here, the human is defining all the rules, and these rules are contained in these so-called knowledge bases. And the artificial intelligence pre-machine learning is dated back to this device called the Wilkinson's duck, which is basically a mechanical duck that was presented at a fair in Vienna, actually, back in 1739, by a French inventor. And he basically stated that this duck will do everything that a regular duck will do. And this is an example of a knowledge base, because all these systems in this particular system of systems is presets. You see that this is just a diagram of what the duck probably looks like. And all these systems are set in place. For example, there is an anecdote about this particular device that actually a farmer came up to this inventor and said, well, ducks actually don't walk like your robotic duck. That's not what they do. At which point, he really has no way of incorporating this knowledge or information because the system is preset. So when we talk about artificial intelligence without machine learning, we are talking about an experience. Here, the experience can be a physical system, can be whatever you're trying to model. There is a human interpretation of this system. And from this interpretation, we just define a knowledge base, a set of rules ourselves. And then this knowledge base is consumed by a computational unit. And then there are forecasts, there are patterns extracted. But here, the key thing is the knowledge base is actually defined by the person. There is no machine learning involved. We basically tell the machine what we want to do explicitly. And machine learning just turns this upside down. Instead of imposing rules, we learn rules and patterns from data. And data is here represented explicitly. And we are not imposing knowledge, but we are just stating that this is the data, these are the set of models, and this is what I'm trying to achieve. And we develop machine learning methods to extract knowledge. So this is completely different than artificial intelligence without machine learning, because the human interpretation here is replaced with feature engineering, which is a term used for manipulating and cleaning your data and also analyzing your data. So this human interpretation piece and the creation of a knowledge base is replaced with preparing the data and analyzing your data through these statistical methods under the realm of machine learning. So this is one of the pluses of machine learning. And when we put this side by side, this is one of the downsides to machine learning, and it also makes scientists a little bit nervous, because sometimes we do need human interpretation. We do need some prior knowledge about the system. We cannot throw away empirical knowledge we had about the way systems of our planet works that was obtained over centuries, and there are important models out there. So more and more we see in machine learning and data science a push towards incorporating human interpretation without biasing it completely with preconceptions of whoever is defining these set of rules. But this is basically the value that data science and machine learning really brings. And when we think about the data scientific approach to problem solving, this is not going to be different than any of you solving a problem on your own. But just to kind of lay out this workflow, we always have the description of a problem and collection of data sources. And for spatial data science, these data sources are going to be spatial and spatiotemporal. And then we have analytical methods. This can be prediction. At the bottom, prediction is just one example, but depending on the problem that you're trying to solve, this can be clustering, this can be anomaly detection, this can be many different things. But here, the key is we are not really starting with a set of methods. We are actually starting with the problem and set of data. And then from there, we're moving on to the methods that we would like to use. As a part of my job at Esri, working with our clients, sometimes I hear, well, we really want to do machine learning. We really want to do data science. And we always work back to, well, what the question is. What is it that you're trying to answer? Because no one needs to just do machine learning. Here, the idea is to solve a problem given a set of constraints with the data that is available. And the machine learning methods, as I've demonstrated from the comparison with AI without machine learning, it just gives us this flexibility to be able to extract patterns without defining explicit knowledge about the system. And this is great because there are certain systems, for example, if you're looking to extract sentiment from geotag Twitter data, we do not have an empirical model that will automatically parse these tweets and just give you an analytical solution about sentiments. You need to extract patterns with a model that can automatically find them. That's why machine learning is so useful for this particular problem where no empirical model exists. But after we are done with this analysis step, we always have the diagnostic step. And after this diagnosis, after we are sure that this model is working using different metrics, the next step is always prescription. We had a problem, we have a solution, diagnostics indicate that this is a good solution. So what should we prescribe? What should we do next? And when we think about the same workflow from a pragmatic perspective, our data sources in spatial data science, they are spatial, they can be temporal, they can even be tabular. And in certain cases, like microblocks, like Twitter data, these can be written sources. But after we have our data, a big step here is cleaning the data, so-called data wrangling. We seek analysis frameworks. This can be something like ArcGIS toolboxes, Python libraries, R packages, and in research, we often create our own libraries. What is important with an analysis framework is this is the trend in machine learning, and this is definitely the trend in spatial data science and machine learning. We never do work isolated anymore. Even the code that we write for our PhD thesis or for our research project, it probably leverages a lot of open source libraries, because more and more we see the rise of, for example, with spatial data science, there's an ArcPy library that has a plethora of methods that doesn't need to be implemented over again. With deep learning, we have TensorFlow, we have PyTorch that have, at this point, more than a decade of active development, at least in the case of TensorFlow, so that there is no reason to re-implement some of these things that already exist. And after the analysis framework is chosen, we basically start working on a relevant set of tools. And what is very important with spatial data science is dissemination, these data products, such as maps, widgets, and apps, because we know that a method really is not very useful unless it is used. And a benefit of spatial data science is everything we do is actually very natural to understand for someone who's not an expert, because things that are spatial, things that you can put on a map, are actually a very natural way of communicating information to start with. So that's definitely is a plus in terms of dissemination and creating data products for spatial data science. So having looked at this kind of life cycle of what this analysis looks like, I just want to step back and I want to talk a little bit from a more theoretical perspective of how does spatial GI sciences and machine learning kind of fit together? How do they complement each other? Where do they intersect, and where do they exclude one another? I'm a big fan of Venn diagrams, so I went ahead and created a Venn diagram for this. So with GI science, we definitely have very important functionality, such as spatial data wrangling, things that we have been doing for a very, very long time, which we might not have called them data wrangling 10 years ago, but we have been doing that. Projections, data representation, discretizations, these are these are the cornerstones of any GI science. And we have been doing that just to represent data, to clean the data, to work with the data, and to process the data to start with. And of course, now the GI science has a lot of direct intersections with machine learning methods in terms of object detection, what I call global models, where we have spatial data and we apply machine learning methods to it. The biggest set of developments in this arena have been things like object detection from rasters, from satellite images. The methods themselves, neural networks, they are not spatial at all. There is no formulation, there is no explicit formulation of space for this method, but it is applied to a spatial data that might be managed inside a GIS, and there is quite a bit of value in this type of approach. And of course, we have the intersection of GI sciences, machine learning, and spatial statistics, which I will talk about in a little bit as well. And here we have methods that are space-time explicit, meaning that space or space-time is explicitly represented in the algorithm. The algorithm knows what came before, what came after. The algorithm has an understanding of things that are nearby versus things that are far away. For those of you who have been working with geographical analysis, I'm sure you're very, very familiar with geographically weighted regression. So this is a very early version of this, where we have the intersection of spatial statistics, machine learning, in this case, a regression model that has an explicit representation of space in its formulation. But of course, we see more and more advanced methods coming up that leverage neural network architectures such as LSTMs and represent space and time for these particularly complex models. And of course, at the intersection of GI science and spatial statistics, these are the research that we have done for a very, very long time. And this is also where I did my PhD, in particular geostatistics. There is immense value in this intersection. We have traditional spatial statistics applied to GIS, such as hotspot analysis, global Moran's eye, kriging, simulations. So these are immensely valuable. There is active research in these areas, and this is still yet a very exciting area of spatial data science. And of course, there is a spatial statistics that kind of excludes GIS and machine learning. And unfortunately, a part of my work has also been here. Well, fortunately and unfortunately, here we are really talking about niche frameworks and empirical models, like the fault model I shared with you in the beginning of my talk. These models require a lot of prior knowledge about the system. They are not necessarily as generalizable. For example, if you're defining a crustal fault network geometry for the particular area that you're working in, you probably cannot apply that knowledge to, say, Twitter data. But these niche frameworks are actually very effective in solving specific scientific problems. And this is the part of the spatial statistics that still remains very exciting. And at the intersection of spatial statistics and machine learning, there are methods that we call space implicit models. So here, the space is implicit, meaning that through spatial statistics, we can create things like spatial subsets of or areas of strong spatial autocorrelation, and we might apply global models in those areas just to remove, just to get away from modeling and space and time explicitly. So these space implicit models, you can think of, just a very simple example is partitioning your data spatially and then analyzing those partitions one by one with a global machine learning method that knows nothing about space. Here, the space is implicit. It's used to subset your data, and the main method can be a global machine learning method. But these models are also very frequently used in workflows, one of which I will show briefly. And in the machine learning realm, that is kind of excluded on its own, we have the general prongs of machine learning, the non-spatial machine learning, classification, regression, clustering. These are very general terms. These are obviously parts of spatial statistics as well, but the way they are formulated and the majority of the applications that you see, they don't necessarily pertain to spatial statistics or GIS, but they are there, and oftentimes we see a lot of value in using them for spatial problems, at which point they actually come to these intersections with GIS and spatial statistics. And just to put a couple of examples on these intersections, the kind of problems that you can solve. I just want to talk about the intersections here. As I said, land cover classification, raster labeling is a growing and also very well-defined intersection of GIS and machine learning in the spatial data science realm. Again, spatial neural networks, spatial LSTMs, they are growing in popularity. There is some research being done on these, and this is where really all three of these methods kind of intersect, and space and time are explicitly represented at the algorithm level. And as I mentioned, we have hotspot analysis and other spatial statistical operators applied to spatial data. And we have the intersection of spatial statistics and machine learning under the umbrella of space implicit models. So just to give a very clear and crisp definition here, spatial versus traditional. with traditional machine learning, we talk about a generally defined methods. These methods do not necessarily require to have time or space represented. You can use them as inputs, but they will not be different than non-spatial inputs. Whereas spatial machine learning methods, they incorporate geography, some measure of proximity or angle, spatial distribution, contiguity, spatial autocorrelation in their formulation. So here, the space is not really an input, but space is actually explicitly represented by the algorithm itself. And this is what makes spatial data science so fitting for many of the problems we look at, where space and time is an essential component, because sometimes representing space and time as just inputs to algorithms actually makes the algorithm perform even worse if you just toss them out, because you might be introducing these latent variables that shouldn't be incorporated as an input to a particular algorithm. And this is where the spatial data science becomes so important. And as I said in the beginning of my talk, this is the very short second portion of my talk. We have a lot of methods out there for spatial data science, many methods that we can leverage. But of course, these methods will only be powerful if we have data that we can run these methods on. And this is not just easy as only finding open data. Here, interoperability becomes a big topic to consider. And the reason for interoperability is different disciplines create different types of data. For example, if you're in the space-time domain, you might be working with HDF5, you might be working with NetCDFs. If you're in spatial domain, you might be working with different OGC standards, you might be working with shapefiles, geodatabases, so on and so forth. At the end of the day, you do not want your analysis to be constrained by these different data types. We would like anything we do, any analysis we produce, to be interoperable. The reason for that is, and this again goes back to the promise of spatial data science, we have many processes operating on Earth. We have natural systems and we have anthropological systems, and more we would like to intertwine these two to really understand our impact on our planet and its systems. So for problems like these, we really need interoperability, because these two research silos did not grow simultaneously. They do not grow in the same way. They produce and process data in different ways. And if you really would like to enable spatial data science in world's biggest problems, interoperability does become a big issue. And that's definitely an issue that we need to consider. So when we talk about an open and interoperable platform for data science, we basically talk about platforms and architectures where we can leverage different standards for data. Examples of which you can see there, such as OpenDAP, JSON, GeoJSON, NetCDF, so on and so forth. And of course, as I said, a big part of spatial data science comes in leveraging pre-existing work that has been done. We do not want to re-implement deep neural networks. Those already have been done before for us. I haven't really touched on R language and Julia. There are big developments in these areas too that you can leverage spatial data science. And again, being able to integrate these to solve these big problems is very important. So being able to interact and integrate different products such as these becomes very important, in addition to databases, so that this can be done at scale. Because oftentimes we have big data and we don't really care about how big the data is. At the end of the day, we want to be able to understand something from it. And for that to happen, we resort to highly performant databases. We resort to high performance computing, such as Spark, Hadoop. So all of these need to be able to be integrated, because with spatial data science, we're really looking for scale, because all these methods are quite data hungry, and we really want to be able to feed as much data to it as possible. So this interoperability becomes a big point to consider if you truly want to do spatial data science that is impactful, so that it can consume different data sources, it can leverage powers of different platforms, and this becomes a very important point to consider. And in terms of open data and this becomes very important for spatial and spatiotemporal data. There are different sources of open data that you can go to for different niche problems that you're trying to do. Our attempt at this has been the Living Atlas, and I highly recommend this. This is, again, available to everybody. This curated data source, spatial and spatiotemporal. This is curated by a community. It's contributed by a community. And this is just one example of kind of like what I call the memory of our planet. These different data sources from different Earth systems, from different anthropological systems, different extreme events that occur. They are all recorded, and they are ready to be consumed as what we call feature services. So for those of you who are looking for open data to do spatial data science on, this is one thing I just want to recommend. And you can see the different types of data that you can find free of charge that you can use in your analysis through the Living Atlas of the world. So this basically is just a point to make where we need performance spatial data science methods, and we have an idea about what these are. And to drive these methods, we need open data, we need interoperability. So I would like to showcase a couple of case studies very quickly, just to bring home the message of how we can use spatial data science. How is it better? What is the value it's adding? And what are some of the problems it's solving? For example, in terms of prediction, one example that we worked on a couple of years ago was climate downscaling. There are empirical models. There are models developed by research labs here. A famous one is called LOCA. And here the downscaling problem is we have simulated temperature at this grid that is discretized by these red points. And we have weather station observations on the ground, and weather station locations are those black points. What we want to do is we want to update the simulated climate at this coarse red grid to a finer resolution using the data from the weather station. So this is kind of like what we call a history matching or data inversion problem, where we have simulations in red, we have observations at these black dots, and then we want to update and downscale, meaning that represented a finer scale, the simulated climate model. And here we used multiple methods. We used geographic weighted regression with PCA. We used random forests, and we actually found that GWR performs very well just because it explicitly represents space, and we know that temperature is a spatial problem. Two locations that are nearby probably will have similar temperatures. Again, prediction of time series is very, so prediction of time series is very important. And here we are talking about predicting the future from the past without using any covariates. Basically, if you have a time series, we have past observations using the trends and cycles in this data. We want to forecast into the future. One thing we can think of is if we have seismometers that collect microseismicity in an area, we want to be able to understand when a big earthquake would arrive from this data. So using the patterns observed in these seismometers, we may want to just extrapolate this time signal into the future to have an understanding of when would a big earthquake arrive, given these past measurements. And clustering, here this is an anthropological example. On the left, you see GPS tags from a navigation app called Waze. And here, by using spatial clustering, density-based clustering, we actually detect areas of high traffic. So this is LA. And if you're wondering, well, where is LA traffic the worst? Well, if you see on the left, it's everywhere. It's just so bad. But with this method, we actually can extract this pattern automatically using this GPS data and spatial and density-based clustering. Here, the advantage is, again, traffic is so spatial. If you have two cars near each other that are not moving that much, but keep on sending a timestamp GPS signal, you know that there is traffic. That is the definition of a slowdown. And a density-based clustering method that automatically incorporates spatial proximity is a great candidate to pick that up. And in this case, it works quite well. We actually tried using k-means on x's and y's, but as you might have guessed, that doesn't really work because all it does is partitions LA into regions, but it doesn't really actually have any idea of a slowdown. So here, the idea of density, something that's very spatial, makes a huge difference in solving this problem. And with classification, we have, as I said, satellite images, and oftentimes we would like to characterize objects on the satellite image. On the satellite image on the left, for example, we have a road, we have houses and trees. If we want to discretize this, if we want to label this particular satellite image using these labels, we actually can use non-spatial methods like support vector machines, neural networks to actually do this type of work. So these were just kind of quick bullet points, and I would like to show you a couple of data scientific workflows where these ideas are used. So the first one is going to be the intersection of GIS and machine learning in the object detection realm. Here the problem is detecting where a certain type of landscape are observed on a satellite image. We are looking for a certain type of landscape, and these are specific type of field, which is a very common problem in precision agriculture. And here we use a one-shot detector to form a relationship between the RGB values of the raster and the type of object I'm looking at. So this is basically object detection. Here, the model we use, the one-shot detector, is completely non-spatial. We actually leverage the PyTorch implementation of one-shot detector. What we do is we have some labels. We give the algorithm the truth. We say, well, in this location, these RGB values correspond to this type of field that I would like to predict. The algorithm forms a relationship between these RGB values and what I'm trying to predict. And then we can, after the training is done, after the validation shows that the algorithm is accurately capturing what we want to capture, we apply this method to a larger satellite image just to find this feature that we're interested in. And in terms of a workflow, we basically have, we start with imagery. We create the so-called imagery chips. So this is when we are really training the model. We create small subsets of the satellite image to create samples. Because in these samples, we will have labels that will inform the algorithm what we're looking for. And we will train a deep learning model. And this deep learning model starts learning relationships between different RGB bands of this particular raster, or however many bands we want to use, and the object we want to detect. And once we're satisfied with this model, we apply it to imagery data to make a large-scale detection, and we can deploy this model at scale. And here are the examples of some of the solutions that can be obtained with this intersection of spatial data science between GIS and machine learning. We can detect things like swimming pools, roads, oil pads, building footprints, land covers, pipelines, certain type of trees, cars in a parking lot to gauge the popularity of a place, road cracks to understand the road conditions at a certain location. So we actually can take a job that can be done by a person, but if you think about tagging all those cars, just a couple of parking lots might take you an entire day to do. And with a method like this, we can actually just automate this process to really extract features. So this in itself becomes a very time-efficient way to find objects and classify a particular raster. And when we think about how does this work end-to-end, in terms of this analysis cycle, we basically need access to imagery. For example, if you're using Living Atlas, you will not have this problem, but you basically need to make sure that you have satellite imagery. We prepare this imagery data, remove erroneous cells if we have them, make sure that all the different rasters, if we have multiple rasters, they're in the same resolution, so on and so forth. So this data cleaning step. Then data labeling. We need to tell the algorithm what we're looking for. And then we train models, we diagnose these models, and if we are happy with these models, then we apply it at scale. And this basically becomes a feedback loop. The more rasters we have, the more classifications we can create. And depending on what we're trying to do, this will induce an action. So this is one use of spatial data science in a real-world problem. So here, for example, if you would like to detect buildings, we can parse this image into these different segments. We can create these image chips, which will basically serve as specific samples that the neural network can learn from. And once the model is trained, it'll detect the feature that we're interested in, and this will be the outcome of this particular method. The other example I'll talk about is a space implicit model. So here, the problem is predicting where a species called seagrass can grow under climate change. Basically, how will the habitat of a marine fauna will change when there's a 2 Celsius increase globally. So the method we use here is we actually define spatially contiguous regions of oceanic conditions, where the ocean conditions are similar in the world's coasts, and then we apply a random forest model region by region to create forecasts. So here, random forest model is not spatial. We use a spatial model to define regions first. We use a regionalization method called scatter. But after we've done that, the actual forecast is done by a random forest predictor, which is not a spatial machine learning method. Here, the space is implicit because the space is used to subdivide our data into different regions to perform this analysis. And we have published this work, presented this work at AGU, and this definitely did, it got some attention in terms of delineating where seagrass what's going to happen to seagrass habitats. And for those of you who don't work in seagrass ecology, if you're wondering why we care about these seagrasses, and as the name implies, these are basically grasses that grow underwater. So an acre of seagrass is actually supports thousands of fish and tens of thousands of invertebrates. They cover about 600,000 kilometers squares, and they actually store carbon dioxide quite fast, up to 30 to 100 times. So here the workflow is we create regions of seagrasses using a regionalization method, and we apply random forest to find relationships between ocean conditions and this particular species growth. And then using a physics model, we simulate temperature increase in world's oceans. And under these new conditions, using the random forest model we trained on step 2, we forecast where seagrasses are going to grow. So in this example, the first step is, as I said, using the scatter algorithm, creating these oceanic regions, and then region by region applying random forest under changing ocean simulations to see, given these patterns where seagrasses occur, where can they occur in the future. Here, actually, we do a spatial temporal study, and on the left is the prediction of our algorithm, and on the right is actually an empirical mapping of these seagrass species. In terms of abundance, you actually see that we are matching quite closely to the observations. In the interest of time, I'm going to skip the last example, but just to talk about this very quickly, the idea here was defining climate regions and using simulated climate data. We basically compared non-spatial to spatial, and when we try to define climate regions using k-means clustering, this is the picture we got. These do not look like climate regions because these are not contiguous, because the algorithm knows nothing about proximity. Whereas when we developed a graph-based partitioning method that does regionalization, which is a spatial clustering method, we actually get climate regions that are very close to the reported ones. And this gives us an idea of what these data-driven regions look like. So without any further ado, I would like to close my presentation by saying that spatial data science is very important because our planet and its processes are inherently spatial. And spatial data science provides parsimony and greater understanding of these processes. Spatial machine learning is impacting sciences in terms of improving pre-existing workflows, opening up new research avenues for problems that we weren't able to solve before, especially multidisciplinary research problems where empirical models do not exist between different components of a system, such as anthropological impacts and their long-term impacts on natural systems. And I will just end my talk by saying that get involved. And one thing I highly recommend is if you're doing research in this arena, there is a research grant between Microsoft and Esri called AI for Earth. You can apply for it. If you get this grant, you will have computational resources from Microsoft, and these machines also have GIS software that you can use so that you can improve and take this exciting scientific intersection of spatial data science to new horizons. And thank you all for your attention.
On behalf of everyone, thank you. We do have time for a couple of questions, and I take it that you may be able to look at the sessions chat to have an eye on questions as well. Let me just pick out one which partially overlaps with a second question. We are from a geography background, typically used to working with geographical data, spatial data in geographical spaces. Of course, many data are in, say, relational spaces, could be image spaces. They are not just geometrically defined. They might just be close and distant relationships between people. Do you have any, can you suggest any approaches how to represent these in an ML approach?
That's a great question. From one research project that we've been working on, we did face a similar problem. And just from our experience, I think a general mathematical framework for this type of data would be anything graph-based and tree-based, because graphs have this flexibility to represent relationships no matter what they are. So we actually were able to combine spatial and non-spatial data into one graph for a partitioning problem, for example. So I think graphs and basically graph-based algorithms are very promising in that regard. And there are machine learning methods that do operate on graphs.
Okay, and actually that brings me over to another question here. Of course, the graph explicitly codes some kind of spatial relationship. It doesn't have to be geometrical, as you pointed out. If we would work with raw spatial data, so where we do not yet have the distance in any domain, in any space made explicit, but just raw spatial data, just coordinate locations of point observations maybe, what would be the preferred or suggested approach with that kind of data?
So as I mentioned in my talk, it's really hard to say what kind of method will work on a specific type of data without knowing what the research problem is, or what the research question is, or what is being expected of this data, or what is the problem that will be solved. But there actually has been, and this is just anecdotal, so I cannot really say that this will work on every case, but they actually show that, for example, an LSTM can learn spatial relationships from raw data without any explicit representation at the algorithm level. And the example they used was actually for extreme weather forecasting, extreme weather event forecasting, where a neural network actually just learned spatial relationships because it basically found out that the closer the points, the similar the signal. And over time, if you have enough data, something like an LSTM can learn that. So LSTM, or long short-term memory machines, are very interesting because they work on multiple scales, as the name implies, long and short-term memory. So if you have multi-scale effects in your data, and if you just want to use raw coordinates without any further representation, that is something that has been shown to be very effective in terms of capturing some of these relationships.
So in a way, bring to the front autocorrelative relationships in one way or another.
Exactly.
One more question here. I'll try to rephrase that a little bit in the context of what we've been talking about. You pointed out right at the beginning that coming here with a stack of data and saying I want to do ML doesn't make a lot of sense. We need to be aware of what we want to learn. So if you look at that from a question perspective, can an ML model learn representations which are not reflected in a hypothesis? So kind of in a pattern detection, finding something I've not been looking for. A different perspective on that would be, am I not biasing the machine learning process through a priori assumptions?
Yes. There actually are a group of methods, for example, under the umbrella of semi-supervised learning, that you give the algorithm some direction about what you're looking for. But as the name implies, it's semi-supervised, that the algorithm can actually completely ignore what you said or readjust the weights of the labels that you assigned. So it'll basically let the data work, basically create those labels. In another way, it's interesting that you bring up hypothesis testing. For example, if you're looking for anomalies, now there are more and more unsupervised methods that can just do anomalies, because in the past, we had to define what an anomaly looked like, either spatially or spatiotemporally. And if you're using GIS for a long time, you can think of a hotspot as an anomaly because it's an anomalously high neighborhood value compared to everything else. But more and more now, there are methods that actually can just detect anomalies just from the entire data itself, where you don't necessarily have to define what an anomaly is. It actually scans through the whole data, it finds structure, and then it finds deviations from that overarching structure. It can be spatial or temporal. So far in the literature, the temporal anomaly detection is actually well studied. So there are methods that can actually accomplish it in the sense of this anomaly detection idea.
No, thank you very much. I'd actually like to wrap it up here, and let me just highlight that I very much appreciated the arc you were spanning up there, starting from kind of a high-level generic introduction discussion where we are coming from, where we are going to, and then illustrating that with impactful examples, including a call to action to get involved. And pointing out these assistance or sponsoring opportunities on the Microsoft and SWA framework. So as we all know, spatial data science and data science is one of the very interesting converging domains. We are discussing this, we're implementing study programs and flavors within existing study programs at our university as well as in many others. And maybe when we have a bit of a curriculum discussion in the not too distant future, we might get back to you on that. But for now, for today, thank you very much. I hope you can carry on into the day with an extra cup of coffee. So thank you.
My pleasure.